I will record, and I think online people can see this. So what we covered yesterday was symmetric encryption. We talked about the general schema of things and that the secrecy hides in the key. We talked about the ideal case where it's a one-time pad and it's completely random, and then it's like impossible to extract any information out of it apart from doing brute force. And then that this is impractical and we have to do a bit of a compromise. So we talked about paths which are shorter and they don't cover the entire message. And we talked about some of the schemas. We also talked about why this is not good enough anymore, and why 2des does not make sense, that 3des is better, and actually gives some extra strength on top of this. We talked a little bit about this one being a modern incarnation of very similar mechanisms, and then we just used a single example for stream cipher. And then we talked a little bit about the different modes, and we have specifically contrasted the one which is not reusing any new information, that every single block is independent, versus 3 types where we feed something into the process such that the blocks don't encode exactly the same thing every single time the same ciphertext is given, right? So you all kind of remember this. All right, so then we're moving forward. Whoops. What just happened? What? I want to share, yes. Volume is up. Yeah, I think we are good. So today we talk a little bit about asymmetric. And asymmetric, as we mentioned yesterday, was invented or sort of designed in 70s. And it kind of opened door for something that has not been possible before, which is we can establish a secure channel between 2 parties without the need for having the secure channel in the first place, right? And we will talk about 2 algorithms. We will talk about RSA, and we will talk about, I think, 1 algorithm, and then we will talk about the Diffie-Hellman key exchange of the handshake, how that works. And then we have to talk a little bit about digital signatures, hash functions, and not only encrypting traffic, but also having an ability to enforce authenticity and integrity of messages. So here is an old news article from 2008. So as I told you, like the slides are kind of old. Most of it is still valid, which is scary. And this article says that the biggest party poker software, which a lot of poker houses online were using, has been hacked because the way they were doing updates was they had party poker sites. So you have multiple sites using the party poker, and then the vendor sort of releases the update to one of the sites, and then that site can be used for updating all the other sites. So not everybody has to go, let's say this is a vendor kind of a server. So once some of them are updated, they can propagate the update further, right? But that meant that if you have a malicious actor pretending to be one of the legitimate poker sites, they can sneak in their own update and they propagate it to others, right? So it's a very typical supply chain attack, which we have experienced in the recent years as well. And it has been used in some of the high-profile CIA cases against Iran, where they injected themselves into the supply chain and sort of manufactured certain exploits, right? So this is like 2008. It happened, and there are some other old cases we will skip. The question is, what was the vulnerability? What caused the problem? So why this happens? So the slide kind of gives it away a bit, right? So we don't have to encrypt all the traffic. Like the traffic does not need to be encrypted. Like we can actually send everything in plain text. What we have to ensure is that the package of what is being sent over, like what that is sent over, the recipient has to validate the authenticity with the original package, right? We have to make sure that what you got and you are updating with is actually what is signed or what is kind of authentic from the vendor, right? So when we download some software from internet and we are updating our Linux now, most of the time, if you have everything configured correctly, there is like an extra check. There is this extra check which checks if the signature of the package that you got matches the published signature of the package that you're supposed to get, right? So that you don't get a fake. Like many years ago, it was not a big deal. The attacks were very rare, and we often just downloaded stuff and we run it. But it turned out to be a very exploitable pattern. So a lot of malicious actors were using it or are using it still. So now we have to be like, you have to do extra step and you have to validate that what you got is actually what you're supposed to get, that there is nothing inside which is like malicious, right? So it is the message integrity which is the key, right? Where else do you feel a message integrity is important? What else do we kind of require this type of check that the message is actually correct? So the message is not confidential. It's just that you want to be sure that it is from the real sender or that it is authentic. Any ideas? So one of the more interesting ones I know of is you have a Sony camera and the Sony camera makes a photo. And then a newspaper wants to publish the photo and wants to say it was actually really taken in Ukraine at that date with that GPS coordinate. So the metadata is actually legitimate and the photograph is legitimate, right? So there is nothing hidden. All of it, like the metadata and the photograph, is all in plain text. It's publicly available. But Sony camera signs the metadata and the image with the signature from Sony saying it was really taken at that spot with those GPS coordinates on that date with that photo, right? And it attaches it, makes it like a hash out of everything and signs it. And then if you get this photo, you can verify it with Sony like public key that it actually is legitimately correct, right? You can do some, you could do some hardware exploitation and try to bypass the security, but because it is done in hardware and because it is sort of in the proprietary chips that Sony releases with their cameras, you can assume quite high level of trust, right? That it is actually, if the signature matches whatever Sony publishes on their website with their public keys, that it is actually legitimate, right? And then there is an interesting phenomenon. We probably will not have time to talk about it, but if you think about it, so you have this journalist. So you have a journalist taking a photo. So you have the photo, and then you have the metadata attached to it. So the metadata is there. The photo is big. It's usually, I don't know, let's say it's like 2 GB, right? It's a high definition, high resolution photograph, right? And then it is with the metadata. The whole thing is hashed and then it's signed. So you have the signature saying this is legitimate, right? And then anybody, like there is you, and this is a newspaper online, and this photo is there with the signature. You can go and check with the Sony that it is correct and it's legitimate, right? So you can have a trust that it is actually correct. The problem is that on the website, you're not gonna have a newspaper article with 2 GB of the photograph, right? Because that would be like amazingly wasteful, right? And it's usually raw, right? The format is raw, and here, I don't know, you want PNG or something, right? So what is published here is different to what has been signed. So now you have a problem. How are you gonna make it possible for me or a reader to verify a PNG image, which is in the newspaper, that it is legitimate with Sony if the camera signed this? How would you do this? How would you solve this? And it's a kind of interesting problem, right? And it's an interesting problem, which actually is a perfect example for the zero knowledge proof algorithms that I talked yesterday a little bit about. Because what you can do is you can generate a circuit. So what you can do is you can generate a circuit, which is sort of like a machine, which takes this raw image and applies a certain operations on it. So it takes it, the first operation it does, it encodes the check for this signature against the Sony public key. So it kind of, it says, okay, I have to first check that this is correct. If this is not correct, I fail. If this is correct, then please resize this image to, I don't know, 480 by 480. Like I'm doing the resizing of this image. Then I'm doing a conversion from RAW to PNG. And then I'm kind of signing the final image with some, like I'm not really, I don't need to sign it. I'm basically generating the final PNG, right? As a final step. And then this circuit is public. I can check, okay, I can see what operations have been done in the circuit. And then this PNG image is accompanied with the verifiable proof that those operations were done correctly. And I can prove to you that those operations were done correctly without giving you the original image, right? So this circuit proves that it was actually done correctly without you needing the original image. And then you have the PNG, and then you have this proof. These proofs are quite short, and the verification of this proof is like microseconds. And you don't contact Sony anymore, but you can verify the proof, and you kind of have that proof attached to the PNG image, right? And the zero knowledge proof kind of works nicely because it does not need the original like image. So this is kind of a nice scenario. It's quite clever, and it is sort of one of the examples of where we need authenticity, and we need to prove something. So this kind of integrity of the message or integrity of this process. So today we're talking about integrity of the messages, like a byte sequence, and we're doing it through hashing and through like asymmetric encryption and signatures, but we sometimes want authenticity of the process, right? We want to prove that certain things were done correctly. And then zero knowledge proofs are kind of a good mechanism for this. All right, so we move on. So we have to authenticate that the computer program is correct. When you're downloading an app from Google Play or from App Store, right? You want to be sure that what you downloaded is actually correct from the vendor. So then you're checking this integrity of the message. You're checking that the binary is actually correct. There is a certain signature that needs to be verified. And like all the mobile apps, they have to be signed by the vendor. And then your mobile phone checks if the signature is correct, right? So you have the vendor, you have the app store, and then you have your phone. And then when you're downloading the app is signed by the vendor, and the App Store makes sure that it is signed. And then when you download it, you can verify with the vendor that whatever you have has not been like manipulated like somewhere in the, on the go, right? Because this thing here is verified with the vendor. This is legitimate, but you want to be sure that what you got from the store is also legitimate. And there can be men in the middle trying to inject something for you. So then you also verify the legitimacy on your end, right? So we often do this. Like we often need integrity of something. Like we kind of don't even think about it, but we often, it's kind of happens behind the scene. Okay, so we kind of need to authenticate that the program is legitimate. We often want to broadcast something to a number of destinations, and then we have a situation where we cannot decrypt the traffic. Like we have, like this the hack with the drones was that you have the source of information, but the source cannot encrypt the traffic because it's not like IoT devices. They are too weak to do full encryption, right? So you have some situation where you cannot like deal with the load. You cannot either encrypt or decrypt all incoming traffic, and then how can you deal with the imbalance? So how can you protect yourself against attacks if full-blown end-to-end encryption is not an option, right? So then you have to make certain authentication process. You have to like legitimize some of the ends such that it will actually work, right? So then traditional single key cryptography uses one key and you have to share it. And if the key is disclosed, then the whole process is compromised. And the parties are equal, right? So you have the source of information, and then you have the destinations. And if it is one-on-one and you trust that, then it's probably fine. But if it is one too many, so you're broadcasting something, all of them are kind of treated as equal because all of them have to share the key that you're using, right? And you have some imbalance. You have some situations where you cannot deal with this way. So you have to authenticate, like, okay, who are you? Like, why, like, is that the correct recipient of the broadcast, right? So you have to authenticate. Or you have to have a mechanism so that the reason, like, again, like you have one and many, then what you could say is say, okay, I mean, we can have multiple keys. Like each of them can have one key, right? I have one different key here and I have a different key here. And that's fine, but we have to somehow share all those keys through all those participants, right? Because those keys are secret. So that creates kind of a complexity. And that complexity often is that we don't do that. We basically share one key. We say, okay, all our recipients, here is the key, and then I will be broadcasting it with this. And that leads to this sort of conflict. So we have, yeah, so here is a couple of questions. Number of keys. If we have X people participating in a network and we need a pair for each key, how many keys do we need to exchange in total? So what is the formula for, let's have a look. What is the formula? I have single participant, okay, there is no need. If I have two, so for two, how many exchanges do I need? I need one exchange, right? If I have three, so for three, how many pairs do I have? How many keys I have to exchange? Two. And then if these guys are communicating, then three, right? So for n three, I need three. So then for four, I need 1, 2, 3, 4, 5, 6, right? So I have 6. So now we have a kind of a sequence. And then can you come up with the formula? Like, what is the formula? How many keys do we need? With the network of n, how many keys we have to exchange such that they can all talk with one another securely? Do you need one more? Let's try one more. 1, 2, 3, 4, 5. So we need 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I miss anything? Can everybody talk with everybody?
That you on the top sides cannot communicate.
These ones. So we have 10. Okay, so you know, and this does not work, right? This one is like a usual suspect. That does not work. What else? What can you say?
Multiply by 2, the number of loops.
So n times 2 looks promising for this case, but does not work in those other cases, right? So, but it's kind of like, yeah, we're getting somewhere, right? So we can say,
You have to add the preceding.
like, because it kind of feels times 2. So what if we say times n divided by 2, then yeah, what do you suggest? Yeah. Yeah. So I don't know. I mean, I cannot solve it because I know the solution. Like once you have a puzzle that you solved, then you cannot solve it second time, right? So and I did it long time ago, so I kind of cannot put my mind into like solving it. But like we have to have um, I don't know. Yeah, I don't know how to solve it. Like, so what did you suggest as a formula?
Not sure what the formula.
Yeah. Yeah. So you want to kind of make it more of a sequence, right? So to solve this one, you kind of add this one to something, right? Yeah, I'm not sure if that would work. Yeah, so let's try it. So for this one, that would be 2 times 1 divided by 2 would be 1. 3 times 2, 6 divided by 2 would be 3. Very promising so far. 4 times 3 would be 12 divided by 2 is 6. Yay, we have the winner, right? It works. Exactly. So this is that's the formula. So we can see that it kind of does not grow like linearly. It kind of grows more like n times n, right? Like in O notation, it is kind of a n square, right? So it actually grows exponentially, right? Even though we're dividing by 2 and doing -1, it kind of the level of complexity is actually exponential, right? It's like in the O notation, we would say, yeah, it's an exponential, right? It's like less. This is like an upper bound, but it still grows. The growth is kind of exponential, which means for large networks, like exchanging the keys is like a nightmare, right? And that's not gonna work. So they have disadvantages, but they have one advantage. And the advantage is most of the algorithms and most of the encryption and decryption algorithms are super fast. So, and you don't want to give that up, right? So we talked about it yesterday, that for streaming or even for some of the block ciphers, you sort of really want to use the symmetric encryption, right? You don't want to do asymmetric because it's fast. But exchanging the keys is a problem. So in open systems, in the systems where n is big, then you don't want to deal with symmetric. You want to deal with asymmetric effectively. Yes, some say that was a major breakthrough, which happened in the 70s. It's like something we didn't have in the world for like 3,000 years. So it's like amazing. Like how can something not exist for such a long time in history? And it's just kind of a concept, right? And then it uses 2 keys and the parties are not equal. So the parties are not symmetric. One of them is the recipient and one of them is the sender. They can make the 2 equivalent situations. So we have Alice and we have Bob. And one will be the sender, the other one will be receiver. And then Bob will be the sender and Alice will be receiver. But so we have some sort of symmetry, but in one, there is no symmetry. There is a different keys used for this path and this path, different pair of keys, right? In the symmetric case, if we have Alice and Bob, we had the key and it was kind of the same key for encrypting and decrypting, right? So the Bob encrypting message to Alice would use K, she would use K to decrypt it and back and forth, right? So the situation is like symmetric. And here we have 2 situations. So the parties are not equal, and it is a clever application of number theory to functions, and it kind of does not replace asymmetric keys. It is not to say, yeah, this is wrong, this is deprecated, we're not going to use it anymore. It's something that kind of complements what we already have. So key distribution was the biggest problem. And then digital signatures. We couldn't sign with this mechanism, we couldn't sign for authenticity, right? We can now with the this asymmetry. And it has been kind of publicly released in 76 by some scientists, and it has been known in classified circles a little bit earlier. So the invention was known, but has not been made public. And then there was like this story I told you yesterday that made it public. So we're using public and private key. And then the public key can be known to everybody and can be used to encrypt and to verify signatures. And then the private key is known only to the single party, to the recipient, and it's used to decrypt the message or to sign it. And it kind of proves the authenticity of the original message, right? And then you cannot determine a private key from the public one. So that's the kind of the main purpose, that you cannot link these two together. I mean, you can derive the public one from private, but you cannot go from public back to private, right? So this is something that is not like that way, does not work. Yeah, so it is as I pointed out here. So Alice can encrypt, but she cannot sign. Bob can sign his messages, but he cannot I mean, he can encrypt to himself, but that not make sense. Like, you know, like what I mean. So it is she can encrypt to Bob, but she cannot decrypt Bob's message when even though she encrypted it. But she kind of knows the plain text because she used it to encrypt it, right? But she cannot decrypt the encrypted message, with the exception of the one she already used. But then it's not really decrypting like she knew what it was originally. And it's the same for here. So he can sign for Alice, and Alice can verify, but she cannot sign. So she can verify Bob's message, but she cannot sign. And she can encrypt, but she cannot decrypt, right? So there are certain things she can do and certain things she cannot do. And it's the same story for Bob, right? So that's why it's sort of, it's asymmetric. Right, so this is pretty straightforward. And then like a little summary, the same algorithm, the sender, they have to share the keys, he has to be secret, and then in practical to find out the key, and then the algorithm is known, and even if you have samples of ciphertext and the encryption text, you're not supposed to find the key. So this is like the requirement for making it secure. And the level of security is like how well this part is done, right? And here we have one algorithm for encryption and one for decryption. There are two different algorithms. Here it's sort of the same. And then they have pair of keys, and they only one part is kept secret, the other one is public. And then the knowledge of algorithm plus one of the keys plus samples should be insufficient to find out the other key, right? So if I have Ali's public key, so I have Ali's public key, and I have a lot, like a lot of messages which are encrypted for Alice, and I still know her public key, I cannot really do anything with it anyway. So I cannot derive any knowledge from combination of those two things, which give me insight into her private key, right? Pretty straightforward. So this is like a diagram explaining it exactly the same way. Notice that now we have this different public and private parts. Before we had key, which was the same for encryption and decryption. Now we have like private and public A and private A, right? So Bob is sending something to Alice. He uses her public key to encrypt it, and then she uses a private key for herself to decrypt it. So this is for encryption, right? For signatures, it's the other way around. So you have to kind of remember it. So so this is for signature, right? So Bob he wrote the email, and then using his private key, he signs it. And then he transmits it with the signature, which is the message Y with his private key used to sign the message. So this one creates a signature. And then what Alice does, she takes Bob's private public key and the signature and checks if it produces the message, if it like matches the original X that she got. And if this X is what she got, that means the message has not been tampered with, that the signature is correct, right? Right. So this sounds good. And you just need to remember this asymmetry on when a source is using a private or public key. So this is again sort of explain the same thing. And now we have a cryptoanalyst analyzing like the information of what is known, right? So what they can intercept and what they can sort of see. So in one way, they sort of see the public keys, and they are trying to reconstruct the private part of the key, knowing some of the information which is kind of exchanged, which is the signature or the encrypted message, right? Okay, so that the previous one was for the signature, and this one is for the encryption, because this one is using the public. No, the previous one was for encryption. This one is for the signature because she's using the public key of A to, I mean, Bob in this case. Bob is using Alice's signature by using her public key. Yeah. And the cryptoanalyst knows. So the cryptoanalyst knows the signature and the public key. In the previous case was the encrypted message and the public key of the recipient, right? So this one is the public key of the recipient. Here is the public key of the sender. And the cryptoanalyst has this information and tries to recover the, in this case, we only try to recover the private key of the sender because the message goes in plain text anyway, right? So there is nothing to break or to recover from the system by the cryptoanalyst besides the private key. In this case, the analyst knows the encrypted message and the public key and tries to recover the plain text message and the private key, right?
Why was the previous example sent in plain text?
For the signature? Yeah, because we wanted, like in this case, Bob sends the message in plain text and sends the signature only together with the plain text message. You can combine both. You can combine this one. So you can prepare Y, which is the encrypted message. Okay, so in this case, who sends Bob? Bob will use Alice's public key to create an encrypted message, but then he will use his own private key to create the signature of the message. So there are two, like this Y is different than the other Y. This one is just the signature. The previous Y was the actual encrypted message. You can send both. So you can send the signature of the message and the encrypted message. And then you cannot check the signature unless you decrypt the message, and then the message is in plain text, and then you can check the signature, right? But Bob may decide to send the message in plain text together with the signature. And then Alice can only verify the authenticity, right? So if the communication is like, depends what you want to achieve. If you want to achieve that the message is sent from Bob, but Bob does not care about privacy, then he signs it and sends in the plain text. And then she can verify it. But if he cares about authenticity and privacy, he can send both. And then for her to verify it, she needs to decrypt it first and then verify it. He can also send it without signature. He can only send the encrypted message, right? But then what can happen? So if I send you an encrypted message, what can happen? Can you be sure that I sent the message? No, right? So if I appear, like if you're reading your inbox and it says, "Oh, Mariusz sent me an encrypted message," you open it and it says something. It is possible that my email address has been spoofed and you got that encrypted message from someone else than me, right? And you cannot be sure that it's authentic. It has been encrypted, it's private, but you don't know if it is really from me, right? So to know that it is really from me, you need both encryption and signature, because then you can verify that, oh yeah, the email address was not spoofed. It is not someone else sending that email. It was actually sent from Mariusz because he signed it, right? And only Mariusz has the private key to sign it, right? So to verify the signature, she needs the signature, she needs Y, but she needs also the X, the original plain text message, because here she will get an X, but she needs to compare it to something, right? Because if like I check, like, so if I, like the process of verification is this. So here is the message, the plain text message. Here is the signature, right? And then here I'm gonna get the signature and the key, and I can reconstruct a plain text message. But I need the original one to make sure that they are kind of the same, right? In reality, because she needs the original message anyway, we typically don't really sign the message itself. We hash it and sign the hash. And then we just say, oh yeah, just compare. If you're getting that message hashed and you're getting that and the signature matches, then it's fine, right? Why we do that? Well, because then like signing something of fixed length is much faster and much more algorithmically better than like random width of stuff that we have to deal with, right? So we typically generate signatures based on something of fixed length. We don't actually sign the movie. We kind of sign the hash of the movie. All right. So then we can have both. So here we are encrypting and signing at the same time from the source. And then we are decrypting and checking the signature on the receiving end at the same time. And then there are two things that are kind of going on. And this person is using their private key and the recipient public key. And this person is like a recipient public key. And this person is using their own private key and the sender public key to do this part, right? So it's like a matching process. So this one is doing both. So it has been developed by those three guys, which you probably heard of at MIT. They were security researchers. They were not working for the military or anything. They were like researching. And they developed this public key scheme that we used until today. The only problem is that it is based on factorization of prime numbers, right? And the factorization of prime numbers turned out to be really easy for quantum computers. The only limitation currently is the size, because the quantum computers have reasonably small qubits to process data. So they are not super big yet. And the whole research is how to make them kind of big enough for practical applications. But once that happens, factorization of large prime numbers will become fast. Yeah. yeah, so you're factorizing the large, yes, correct, yes. So, but until that happens, this is a really good mechanism. And then we kind of using large numbers to start with. And then, we are relying on this factorization kind of which operation, which is reasonably hard to conduct classically, right? There should be, I should have some tables. So this is like how big numbers did we factorize until May 2005. And I have an update. Yeah, I will show it after the break. So I have an updated table, what has happened after May 2005. So we can have a look. All right, so you know it? Have you had this before? So I'm gonna sort of like, what's the time? Yeah, so let's have a break. I will bring the bigger table with the latest factorizations, and then we will continue. So let's have a break. Yeah, let's do 15 minutes. Yeah, new window. 15 minutes. All right. Great. So we are back in the recording. Okay, so let's talk a little bit more. Like, let's see what we have in stock for us. Diffie-Hellman key exchange. So did you had it before as well, or you didn't have? Yeah. So why do we need a key exchange scheme for? What is it used for? Yep. Exactly. So we need some sort of a protocol which allows us to establish a secure channel and then pass a symmetric key over that secure channel, and then we can start communicating over the secure channel. So the idea is very simple. And once we knew about public-private cryptography, we could kind of do the key exchange, right? So it's a public key distribution scheme that allows us to exchange the secret key and then start encoding everything else. So it is not for exchanging messages. It is not for encrypting arbitrary message. It's just for establishing a single symmetric key. And then this key is only known to those two single participants. And it has a bit of math behind it. So I'm gonna skip the math. Okay, more math. So man in the middle. What is a man in the middle attack? So this is describing, but the concept is you are trying to interject yourself between two participants, and you're trying to pretend to them that you are like that they are. It's sort of like the Microsoft with end-to-end encryption. It's basically the same story, right? So that's the man in the middle. Okay. So we already discussed it yesterday. So okay, so then we sort of covered the basics of symmetric encryption and Diffie-Hellman very quickly because you had most of it before. And then message integrity and message authentication. So we do have like old-fashioned techniques for error detection and error correction, right? Where do we use error correction? Where do you think we're using those mechanisms. And yeah, cool. So some lossy channels. Yeah, good. What else? You are using it like all the time. Where? Where do we use it like all the time? Yeah, exactly. So RAM, disk, right? Every time we need bulk data to read, there might be problems. So with RAM or with disk, what happens? So if we're reading something from a disk and there is a problem, we kind of need to read it again, right? And it's the same with RAM. But with disk, it's like very common. And almost every platform is sort of implementing some form of CRC or error code correction, just in case, right? I am not sure now, like for HDDs, that was like 100%. Like you always have to check for like the latest, like the NVMe drives or some like solid state drives, so SSDs. I actually don't know. It would be nice to check whether we always do 100% as well or not, because with RAM I know for sure we're not doing 100%. So for commodity hardware for your laptop, we say actually we prefer things to be fast, and we trust that RAM will not lie to us, that the bus and the RAM will always give us the correct values, right? So for RAM, what we do is we say, okay, let's assume it is correct and let's continue, right? And what happens is, if your RAM is a little bit faulty, what happens then? Your system misbehaves, right? Your OS like have glitches. You have a blue screen of death or something, right? And you don't know why. So some bad things will happen, right, on your laptop. If you're running a server and you're serving 1 million customers, or if you're in a telco company and you're routing calls and something and your RAM misbehaves, that's a serious problem, right? I mean, really bad things can happen, like people may die, okay? So we have RAM, which is checked and which has this error correction built in, and it's a special RAM. And then you have buses, you have motherboards, and you have cards which have that feature enabled. And you can enable it, and it will do error correction on the fly. What it means, it will slow down a little bit the reading from the RAM, right? Because it has to read from the RAM, check if the checksums are correct, and then continue if they are fine. But it will catch mistakes, right? It will not misbehave if the RAM starts being flaky, right? I was working as a lecturer in another uni in the lab, and we had about 50 computers. It was back in a day where the labs were with computers. And two of them, like students were always complaining, like it was like randomly shut down, or it was like, misbehave, like some weird things will happen, right? And we investigated, we checked, like first, of course, we suspected it's like human error somewhere, like they typed something wrong or whatever, right? But it turned out actually in both of them, one of the RAM chips was faulty, and it like sometimes it just misbehaved. And it was like really, really difficult to debug. I mean, once we sort of suspected the hardware and you run the hardware test, then it showed up. But we didn't, like, it didn't occur to us to immediately check the hardware first, right? We thought it's the student or the human. Then we thought it's the OS misconfiguration. And then we, like, after we checked all the software stuff, we said, yeah, it looks like it is not software. It looks like it's actually hardware. So we using those for hardware checks. So why cannot we use the same techniques for detecting that something has been maliciously changed? Can we? Like, can we use similar techniques to check if something has been changed? Yeah, to some extent we could. So if I send one of you a message and then I calculate like some sort of a redundancy check on it, and then send it to you, and then send the check like off channel to you as well, so you can check that my message was kind of not manipulated in the middle. What can potentially happen? So what we do is, like, you have the sender. The sender prepares the message and then calculates some CRC code for the message, and then sends the message. So I send it to Bob, and then I kind of off the channel send the CRC to Bob as well. So Bob can use this CRC to validate my message. What can happen? So there are two possible scenarios. One scenario, you have man in the middle, and the man in the middle can observe the CRC and then observe the original message and inject herself or himself into preparing a new message which matches that CRC code. Right? Is it doable? Is it doable for the attacker to find a new message which matches that CRC code? It is kind of trivial, actually. So finding a message with the CRC collision is kind of a very easy task. I usually just rely on some bit counts, and then you just, by creating a fake message, you just have to pad it with something which will result in the CRC being correct, right? So this is kind of an easy task to do. So that means it's easy to spoof a message, right? So using CRC is not gonna be very robust in this situation. So we sort of need something stronger. So what stronger mechanism can we use?
Hashing?
Hashing, exactly. So I can create a hash of that original message, pass it to Bob. The attacker can observe the hash, observe the message, and now the attacker has a task of spoofing the message with a given hash. And we know finding that collision is not a trivial task, right? So if the hash function is shed, it is possible, but normally we don't use hash functions which are easy to do this. So that means the attacker cannot like really do this. And we have a second situation, because me transferring the hash to Bob is a bit of cumbersome process, right? So if I have to do it off chain, off the band, off band, I kind of don't really want to do that off band. So what I will do is I will sort of try to send this together, right? So what can happen now? So I'm sending my hashed message to Bob. Man in the middle catches it, and then what can happen? The attacker creates a new message, hashes it with a new hash, and gives it to Bob. And Bob checks it and says, oh, yeah, it looks legitimate. The hash matches, right? The hash matches the message. So that situation is like worse, because it's trivial for the attacker to fake something from the sender to the recipient by just like faking the hash, right? So we need something which links the check, the hash, back to the original person, like back to the sender. right? And that's why we have this sort of like modern mechanism, which allows us to sign something with the private key of the sender, such that the attacker in the middle cannot really fake it completely, right? There are certain types of attacks that man in the middle can still do, but not like if Bob knows my public key, then the attacker cannot really do anything, right? So using one-way hash functions. So one-way hash functions have certain properties. So one property is that they compress a larger domain to a fixed length of bits, and they should be easy to compute. So they are fast to compute and fast to check. But they have like many to one, which means many messages can map, so we have the collision, right? So is the authentication and integrity provided by hash functions themselves? No, the integrity is, but the authentication is not, right? So the integrity that this content matches the hash is provided by hashing, that this content matches the hash, but not the authenticity, right? So yes. So the hash functions don't generally contain any keys, but we can kind of have a specially designed hash function, and we can include something the way the hash is generated in such a way that it uses kind of the key, the additional mechanism, right? And then we have those called message authentication codes, MAX or HMAX, which we often use for authentication in the REST APIs, right? Okay, so this is a little bit of a theory. If we have, yeah, we can skip this. So then, like, the only difference is this one's kind of a hash the original pre-image without any additional information. And here we have something extra. So we have kind of a pair of things. So instead of just a hash function hashing the input to output, here we say, yeah, it's kind of hashes the input to output, but there is this extra information. And then you can sort of verify only if you are kind of using that extra information. Right, so you have variable size input, yes. You have fixed size output, yes. You have to be relatively easy to do the computation. You have to have this collision one-way property strong. And then, so you cannot find what the original one was, and then you cannot find another one which makes the same hash. It should be, so you have a weak resistance and strong resistance. The strong resistance is that you have computationally infeasible, and then what's this one says? Yeah, so this one is that for a given hash, you cannot find the collision. This one says, in general, you can find a collision, right? This one is basically saying you can pick anything you want, you can hash it, and then it should be still as hard as with anything else to find a collision, right? This one is saying for a concrete hash, it should be hard to find a collision. You understand the difference? This one is stronger because it allows the attacker to pick whatever they want to hash and demonstrate that they can break it, right? You see the difference between these two? So, like, if I have a hash function, so I have a hash function and I have a certain hash, and I'm saying, yeah, for this hash, it's really hard to find a collision. It's the soft one. If I say, okay, I have a hash function, and then I say, I don't care for which hash. You just pick whatever you want. You are the cryptoanalytic person, cryptoanalysis, you're conducting cryptoanalysis. You can pick any one you want, and you will still not be able to demonstrate that there is a hash, right? Like the only difference is like in theory, because in practice, like we always sort of talk about this one. We kind of don't talk about this one because it sort of does not make sense. But if you think about the keyed one, and if you think about like hashing something just for one off thing, then you may just want the type of hashes that are infeasible to find a collision. So you may be interested in the weak one, right? But in general, if we're talking about hash functions in general, we always want this one. And then this one is an interesting one. So you want the hash to actually look random. And why is that? There is another formulation of this requirement. So if I have hashed something and I have the bits, they should exhibit like random distribution. Why is that? So what, okay, forget about this requirement about randomness. So what is another requirement that you would like to have your hash function? So if I have input, I have some sort of input, and it's bits, right? And the last digit is 0, and I create a hash. So now I create, yeah, let's do it this way. I created a hash, which is fixed length. This one is much bigger. You see the dots. And then you have the hash. And then I flipped it. I flipped it to 1. And I have another hash. Okay. And now I'm comparing this hash with this hash. And I'm asking question, if I flipped 1 bit, how many bits have those two differ by? Why? Yeah, exactly. So, but why 50%? Where this 50% comes from? So it kind of like conceptually, if you think about it, it comes to a fair coin. If you're tossing a fair coin, what is the chance of getting 1 or 0, or heads or tails? 50%, right? So you have no knowledge, like there is no bias, there is no structure, right? So it means if I'm flipping bits, then I should have exactly the same, and that gives no information, right? If it was 60% or if it was 48%, that would leak information. But 50% in terms of binary operations, that means I'm just flipping bits, right? So it basically means I have like roughly half of them changed state. If it was more than half or less than half, I would have structure. I would have something to exploit. But because it's exactly half, I have nothing. And it's the same about the distribution. Like it should be random, uniform, and should not have structure, right? Because if it does have some structure, there is some leakage. There is some link that allows me to establish that link. That link. So in information theoretical like that's where Claude Shannon comes in as well. If you have a message, like if you have, yeah, it's again a little bit abstract. I don't want to go into the math and into the logarithms, but if you think about it, if you have a channel, right? So you have some sort of a channel, and this channel generates a message for you, right? And the message is, yeah, let's say 4 bits long, right? So this channel generates a messages for you, and there are 4 bits, and there is like 50% chance that this one is 1 or 0, 50% chance this one is 1 or 0, 50% chance that this one, and 50% chance that this one, right? So you have like a full randomness in such a way that you cannot tell, like everything is like utilized to the fullest, right? So it's like fully random, right? So how many possible like messages can you get out of this channel? It's like the maximum, right? So I have 4 bits, so it's 2 to the power of 4. So it is how many? 16, right? 16 possibilities. So now you can get out of this channel all 16 because all of them are equally kind of probable. So now if they are not, you like, but this means this one is like the full channel, and there is like I cannot compress it, right? I have all 16 messages and I cannot really compress it anymore, right? But imagine that I have a situation where like 80% of the time I'm getting this being 1, and 80% of the time I'm getting this to be 1, and 80% of the time I'm getting this to be 1. And then half of the time this one is 1 or not, right? So now I have a slightly different situation. I know that certain messages appear much more frequently than others, and then some messages occur like very little. So 000 occurs like very, very limited number of times, right? So what I can do is, like in theory, I can see if I'm still getting all the possible messages, and if I do, I may still need 4 bits. But if we have a situation where this one is like much longer, so I have kind of a much longer sequence, and some of them like only have ones, or some of them like have really close to 90% ones, I can kind of analyze it and I can like recode it in such a way that I can potentially have less, like I can squeeze this channel, which is currently using like n bits, to kind of a smaller channel, which has more or less 50% on everything, because I'm kind of squeezing the information in. But like it is a little bit like I'm trying to like explain the intuition. So if you have like if you have a person who yeah, what could I use as an example? Because you kind of need more than just 1 bit. So if we just have 1 bit, you always have to have 1 bit. But if you have multiple bits, but some of them are kind of almost never there, then you can kind of encode that situation in a slightly tighter way. And what it means is you can kind of squeeze the channel in such a way that for messages that like almost never occur or never occur, you're kind of allocating less space than you need. Okay, so I know one example is this. If we have an alphabet of 24 characters, how many bits do we need to represent that alphabet? So 2 to the power of 4 would not be enough because that's 16. So we need 5 bits, which is 32, right? So we kind of need 4 bits to represent all the letters, right? So if I have a message, so now I'm talking like messages, and I have multiple letters. So let's say I have, I don't know, big fox, right, jumped, something. So now I kind of need to encode it in such a way that I kind of like, so maybe space I need 25, right? So then if I'm, for every character, I can use 5 bits, right? So I'm saying, okay, 5 bits for B, 5 bits for this one, and so on. But we know from the alphabet that not all of them occur in the language, in the English language, with the same frequency. We know letter E or T appear much more frequently, right? So what I can do is I can say, okay, I can encode the most frequent letters using less bits. I will just give them 4. So in the 4, I will have the most frequent letters. And then with the bigger one, I will kind of use more space. And I'm kind of squeezing the ones which are not so frequent out of the equation. And I have to have additional mechanism to sort of flip which one is which. I need some extra padding, right? But if you kind of do uniform for everything, then you will be wasting space. But if you squeeze, you will be kind of benefiting from the frequency, because even though the other ones might be a bit longer, the shorter ones will kind of be more frequent. So then you can kind of encode the message in a more compact way. So you can kind of compress it without losing the information. We can always compress with losing information, but we want to kind of compress without. So then we can kind of benefit from the properties of the actual messages. But in cryptanalysis, it's exactly the same. Like if there is some form of structure, you can kind of discover it and exploit it. So what you're trying to do when you're designing those things, you're trying to make sure that there is no structure, that you have to use all the bits, and it kind of always is just like random coin toss, right? So you want each bit to be as likely to be flipped, and you want to have this avalanche property, which causes, on average, every bit flip to flip like 50% of the other bits, right? On the hash. So it kind of goes back to Shannon guy. Like he sort of laid the foundation, and he laid all the like channel metrics in such a way that we can calculate what does that mean. And every time you violate the 50% or the binary like flip of the coin, then you're leaking information, and it can be exploited. It means there is some form of structure, right? So if I have a really good compression algorithm, which takes let's take text, and it compresses it to a binary bits, right? What can you tell me about this process? So we are compressing. So one thing that you can tell me is this one will be bigger than this one, right? For text is almost always the case, right? Why? And then let's take, for example, a binary image of a hard drive. So why for text, the ratio of this to this is always much nicer than for the binary image? Because there is structure. As we discussed, there is a lot of like padding, a lot of zeros. Like we're using 8 bits for something that not necessarily needs 8 bits. A lot of bits are not used ever, right? So if we're only using alphabet of 26 characters, but we're using 8 bits, which is giving us 256 slots, a lot of slots are never used, right? So we don't need 8 bits. We can encode what is used in a smaller way. So that means this will be much smaller. Here, that's not the case. Like the binary image of a hard drive is using all the 8 bits almost uniformly, right? All the bits are kind of used up, right? So if we try to compress it, it will work. There is still some structure, but it will be kind of a small ratio, right? This one will be much bigger ratio. What else can you tell me? What can you tell me about statistical properties of those bits here? That they look random. There is a probability of 1 or zeros is like half. Like all of them looks like a random toss coins. There is no structure, right? So then if you try to compress it, second time, what's gonna happen? So if you try to compress this again, what can you tell me about the size of this and the size of this? Or worse. So in the best case, it's the same. But normally this one is worse than this one, right? Because it assumes there is structure, but there is none. And it tries to generate those extra, dictionaries and stuff, but there is nothing to exploit. And it ends up being bigger than the original because there is nothing to exploit, right? So if there is nothing to exploit, that means you cannot kind of recover any information from this because there is no structure. So it's the same with the hash. Like if the hash has this property that this looks random, uncompressible, and no structure, then it's very hard for crypto analysis, right? There was a lot of hype about encrypting, no, not encrypting, about compressing hard drives. Did you ever compress the hard drive? Not really, right? Why not? Would it make sense to compress your hard drive and to gain a bit of extra space on your hard drive? Well, in the old days, it did make sense. I mean, my first hard drive was 20 megabytes, okay? That was my first hard drive. And it was kind of small, right? So it kind of made sense to use compression to gain some extra 5% or 10% and so on. But compressing hard drive has this property that it's sort of like diminishing returns. I mean, the more stuff you have on your hard drive, the more random it looks and the less you gain. And then you're wasting a lot of like resources, like time, because reading something needs to go through compression and decompression, right? So then you sort of not like gaining anything and you're losing time. So these days, the storage is so cheap that the compression of the storage became sort of a no game, right? We were not encrypting the hard drives before because the CPU and RAM was so slow that would kill performance completely, right? But now we sort of in the stage where almost all hard drives are encrypted because it's relatively cheap. You have dedicated chips to do the encryption, and it gives you a lot of like protection and a lot of privacy. So it's kind of interesting to observe like how it flipped, like from something that was actually not that useful, like compressing a hard drive, to something that is like giving you privacy and it's like built in. All right. So we also use hashes for not storing passwords in the plain text, but storing the hash instead. And why we do that? Why it is a sin to ask a user for a password and then store it in a database as a password, like as a text. Exactly. So you want to protect yourself from a breach where somebody unintentionally, maliciously got access to your data store. And then the data store contains just hashes, right? So if your data store contains hashes, so the flow is like this. You have a user. The user wants to log in. So they establish, so they like enroll. So they establish a link with the password. And here we store the hash of the password. And then when the user logs in, they pass the password, but they don't need to. It kind of depends. Sometimes the hashing happens on the client side, sometimes it happens on the end. But let's say it happens here. So then the system takes the password, hashes it, compares it with the hash, and then grants access or not. It also is useful to have some sort of salting mechanism. So there is some kind of a hash and some sort of a salt being used for the hash, such that it's like not just a plain stuff of that password, but something extra as well, right? So now the attacker got those hashes, and then the attacker is kind of left with brute forcing, trying to find the collisions, right? If they find the collision, so let's say the original password was password A, and the attacker finds password B, which collides with that hash, they can use the password B because then it will kind of work, right? So they may not know the original password, but they will gain access. And that happened, like it actually happened when I was teaching the course that Linux originally was storing all the user passwords with MD5, MD5 algorithm, right? You heard about this algorithm? It was the only one Linux was using. And then I don't remember who found that it's actually relatively easy to brute force the collisions on the MD5 file. And then it was like, oh my God, we have to change. Like you cannot use MD5 in Linux anymore, right? So everybody had to update and kind of change the hashing mechanism to a different one, which was stronger to store the user passwords. And we did like the John the Ripper on MD5 files, and we could like really crack our own passwords back in the class. And it was kind of cool to sort of like actually like be living that at those times. So yeah. So then, right. So we already talked a little bit about using the additional information for using hashes for message authentication. And that means you are kind of hashing the message and then using additional thing such that on the other end, you know that additional thing, and then you can validate that the source is actually legitimate. So you're not only using the hash alone, but you're also using something that belongs or is secretive with the sender. So you remember this picture with the man in the middle hashing something? So that basically tries to circumvent this type of exploits. And those are the different schemas that we can have. The idea is basically always the same. So the idea is that you kind of include this extra key. In this case, the key K is symmetric, right? It's sort of used for encryption and decryption together with the hashing of the messages. Again, we're not gonna dive into the math of how the hash functions work and how they achieve this 50% of impact on the bits. It kind of, again, goes to this sort of assembly of like how the crypto systems work. You can go there, but it's similar to the encryption mechanisms. We're using a lot of that information, compression, such that we trying to combine certain structure into stuff that doesn't have structure, and then the diffusion. So you're trying to, like, by the nature of the hash functions, you're always compressing it because you want to achieve a smaller length, right? But yeah. So here is like a simple example where you can try to use a simple XOR function to build up something that kind of hashes a larger content to a fixed length kind of struct, right? And you can kind of invent your own hash function, but then you have to investigate the properties. So the one which is using XOR and doing this bit by bit kind of a compression of the structure into a fixed length is like one of the simplest ones, but it is not secure. And it is kind of useless for security. But if you want, it is kind of like the CRC code, right? You can easily calculate whether the thing was like, it will work. So if you have a message, it will produce the hash, and the hash will match the message, and you can check, oh yeah, it verifies. So for verifying it, it's kind of fine. The only problem is that it's kind of really easy to reconstruct something or to fake something with the same hash, right? So like it does not have the security properties that we are looking for, but for verifying the data integrity, it's good enough. It's the same as the CRC code, for example, right? The parity code. All right. So then you have again two types of attacks. You can say, yeah, I don't know, like let's throw it to the cluster of GPUs and let's kind of crack it. I will stop recording. So I have, okay, so we could do a simple hash function reusing some of the symmetric encryption mechanisms that we've used, because they've used this concept of a block and they were kind of doing a rounds over the block. So we can kind of take the input, use this block, do the rounds, and kind of keep doing it until we finish the incoming message. And then the final block will be the state of the final block would be the hash, right? So instead of like kind of compressing the information, encrypting the information and kind of combining it to the final encrypted ciphertext, we sort of doing it in a cycles such that we end up with this final block, which in our case of the like death would be 64 bits long, right? Would that work? So would that produce the kind of a hash function for a message? It would. Would it be easy to cyber analyze it and kind of reconstruct back what the original text was from the message? From the final block, 64 bits? It would be hard to kind of revert it back, but what is the problem with 64-bit hash? Collisions. Yes, it's much far easier and faster to find collisions because there are much more collisions with the squeezed 64-bit space, right? So it is fine. Like the idea is fine. It's just that the key, the final length of the hash is too small. We need similar mechanism, but we need like larger block of which is being used. So then that's exactly what the hashing algorithms do. So 93, the development of secure hash algorithm. I made a mistake yesterday. I said 128, it's 160, not 128. And that was the first SHA, which was used for about 10 years. And after 10 years, in 2005, that when the collision was found. And we cannot, it's not really recent, but so we don't use SHA-1 anymore unless you don't care like about cryptographic properties. It's kind of funny because we often don't care. Like we, for example, when we test things, we don't care about using cryptographically sound random number generators. We can use something that is unsecure. There are many situations where doing a strict requirements on security is not needed. Maybe what you're doing is you're working on some hash table and you need to use hash function. You don't necessarily have to use a cryptographically secure hash function for this use case, right? So it's not always the case that we have to use the cryptographically secure mechanisms. But if the security is concerning, then we should not use SHA-1. And then there is a whole family of SHA functions, and then they're represented by the number of bits they have as the final block. So they work in a cycle, similar to the one which we explored with DES. So it's very similar, but instead of using 64 bits, they basically use 124. So they use 124 bits and they kind of do this sort of like a cycle going over the message and then like encoding it like 124 at the time and then combining it, like squeezing it to a certain length. So like SHA-512 will kind of squeeze it to 512, feed it back, feed it back, feed it back, and then the final one is like 512, which is the result. So it is kind of like the schema is very analogous to doing the cycle. It's just that we are using cutting the message into 124 and then like additionally squeezing it to the 512 blocks, which we sort of pass through. Like it is similar to this mechanism of CBC, where we had this kind of additional vector being used for calculations. You remember that? The diagram where we had the block, but we are feeding additional information in. So here, that additional information is 512. And then the final one, which is the additional information which we're supposed to feed, is actually we don't feed it, we just use it, right? We're not using those, we're using that kind of IV so the compression or the encryption happens on that level. For the hash, we're using that level, right? We're using the additional information that is sort of fed into the process. So would that work if we were to have SHA larger than 124? Or do you see a problem of going beyond 512 or beyond 124? So the problem is that the magic happens in this function, right? The magic happens in this function, and this length is the major source of randomness for us, right? So because initially we use 0. So the H0 is like, it's a constant. Like we actually don't have the source of randomness here. We have the source of randomness being the message itself, right? And then this one is deterministic. And then it starts feeding this randomness through this extra function to get this, and then feeds it here. But the source of randomness is not the IV, is the message itself. So then if this one becomes like smaller compared to what we're doing here, and the hash is like 248, we probably gonna observe some structure. We're gonna start leaking something because the structure comes from this level. So we cannot really go beyond 124. Well, like we have to expand this part to have extra randomness into each of the iterations, right? So we're not likely to reuse that for more than 512, but if we make this bigger, then we can continue with that same mechanism. what is the problem of making this one much bigger? What will happen then? Like, what will happen if this one is like quite large? What will happen? We kind of like this property here. We like this multiplicity of the 124. If that 124 becomes quite big, the n will be kind of smaller, right? So we will reduce the number of rounds that we have to do, and that will again introduce possible exploits. So we like to have the multiple rounds because they have this kind of confusion and diffusion property. If we just are doing one round, then it is sort of like easy to brute force backwards, right? The diffusion and confusion properties are sort of missing. So we kind of cannot go too big internally because that reduces the number of rounds that we sort of do. And that also influences the way the structure of the hashing for this case works. So it's a tension between like how much randomness comes from the message and how much structure comes from the message and how much randomness comes from this F, which conducts this confusion and diffusion process on all the bits, right? All right, so then there are the details of how it actually happens. Like we have to do some padding, we have to initialize certain things, and then we kind of conducting those rounds. I'm not gonna read the slides, so you can check and you can check how the operations in the circuit are performed, but it's very similar to encryption. So it's the same mechanism that happens sort of in the F, which kind of takes the bits and runs this kind of a confusion diffusion mechanism. So I'm not gonna kind of talk about it, but like you can see all the n rounds, all the rounds kind of happening here, and then we repeating the process additionally like multiple times. So for SHA, we are doing 80 rounds. So this is the summary table. We for SHA-1 we're doing this like 80 times. And then we say we have kind of a security metric of what that means. We have the length of the block, which is the remaining one. We can see that for the like 512, we're using 124, but previously we used smaller one. So this block here was 512 for the smaller SHA functions. But then it has to be expanded because for the properties we just discussed. So you can see that since like 384 and for 512, we expanded the window to 124. We were getting too close to the size of the actual window. And then if we want to grow, if we want to have a bigger blocks, we have to grow this window as well. You also observe that we changed the word size. We were operating on the 32 bits at the time, and for these ones, we operating 64. Why is that? Could we also do 32 here? We could. It would just be inefficient. It would be a little bit more time consuming. And because we have 64-bit architectures, modern architectures are 64, we're using 64. So if we go bigger here and bigger here, we're not likely to change that parameter because that fits very nicely into our architectures. Unless we start doing something on like 128 architectures, we're not likely to change that parameter here. It kind of comes from the architectures that we're working with. And then the number of steps, we were kind of, we had a setback, you could say, and we went back to 80. So for this, we observed that even reducing the number of steps was not influencing the security parameters. So we could do less rounds or less steps and still keep the security parameters quite high. And we kind of went back to 80 to make this kind of adjustment. So then we talked a little bit about the MAC, like how the MAC information is attached to the message with the key. So I'm gonna kind of skip this a little bit and go to the not the mechanisms. Yeah, not this one either. So this one either. To digital signatures. So we kind of had those and we standardized this one for internet. So we are using HMAC, as I say, most of your tokens, like most of your authentication tokens are kind of like HMAC based because it's quite simple to compute and it's quite robust, and you can use different hashing functions depending on your requirements and your security guarantees. So it's quite a comfortable and robust mechanisms to use. We don't need to look inside. And then we are talking about the digital signatures. So like how can we not only verify that the message is actually authentic if we have the same key, but if we can verify a little bit more, like verify, additional metadata and verify kind of more information which comes with the signature itself. So we kind of expanding the previous mechanism just for the authenticity of the message with this kind of a digital signature scheme. So we are using Bob's private key and the message to generate the signature, and then we attach the signature to the message and send it to Alice. So Alice gets the message as a plain text, and she gets that signature, and then she can check if the signature matches, like if all the checks are kind of pan out. So she will use the Bob's public key to validate that this green box is correct, that it's what actually happened on Bob's side, right? So it's like a schematic of what the digital signature offers us. The message travels unencrypted, right? So if we want to do it, we usually take the message, calculate the hash, take the hash, encrypt the hash with Bob's private key, and then we have the signature. So this one does not have any, like, we're not using the additional things and the date and time and so on. We just kind of, for this schema, we only using the message, but you can imagine that like other parameters can use in the same way. So the S is effectively an encrypted hash of the original message, encrypted with the Bob's private key. And then she will take that S, she will decrypt it with his public key, right? So we are kind of piggybacking on the public private key encryption decryption. Here we reversed the keys. So he used his private key to encrypt it, and she uses his public key to decrypt it, right? And then she will get the hash, and then she will get the like plain text message. She will calculate the hash, she will compare the hashes, and she will say, yep, all is sweet. So we already discussed that. This is like the more mathematical like view of the same process. So he calculates the hash, encrypts it with the private key of A, combines those two, his like plain text message and this encrypted hash, passes it here. This is the encrypted hash with his private key. So she decrypts it with the public key and then compares. She needs to hash the message as well and to do the comparison. So those two diagrams are exactly the same. It's just that we sort of annotated it with this more mathematical notation. And here we are combining confidentiality with the digital signature. So we not only want to say that message has not been tampered with, we also want to say that message can only be read by Alice. Or by the recipient, right? So, and here we kind of combining it, like we're doing the same process, but we are encrypting the final thing with something that the recipient and the sender share, right? So then it's like encrypted and signed. So it's like confidentiality with authenticity. All right, so then that's it. Any questions? We covered this already, like we just repeating ourselves here because we already discussed the digital signatures. The important thing is not to confuse confidentiality, which is encrypting something, with authenticity, which is validating who sent that original message, right? You can get something encrypted, but it might have been encrypted by the attacker. And it will be encrypted and you can decrypt it, but then you don't know if it was sent by the original sender. So by being able to encrypt it and decrypt it and check the signature, you have both. You have authenticity and you have the confidentiality. Confidentiality does not carry the authenticity or verifiability like automatically, because anybody can take your public key and encrypt it for you. Only you will be able to read it, but anybody can do it. So if you want to know that it was from a specific person, that person needs to attach the signature as well, right? So that's the most important kind of aspect. And with the private public key cryptography, we can achieve both, but those are two separate processes. It's not one. And also by me signing something, it doesn't mean the message and like travels encrypted. Me signing something just means you can verify the message, but the message travels in plain text. So I need to combine it both. All right, so I will finish here with the lecture. I will stay here and I will work on the exam, and then you can stay here and work on the compulsory tasks, and you can ask me questions if you need some clarification or something, right? We will meet next week on Tuesday, and we will start blockchain. So again, I will have a lecture because I need to tell you a little bit about stuff. And then I will give you some tasks to work on. But we will be starting on Tuesday with the lecture, which will be in Zoom and will be recorded. The more practical things will come in the second half of Tuesday, and then Wednesday and Thursday. We will do more work. The work that we will do will be a little bit different to the work that we are doing for this module, because we will be working with transactions and we'll be working with explorers and we'll be a little bit more interactive. So I will give you something, you will try it, and then I will tell you what the correct answer is, and then we'll move on. So it will be a little bit like try to do this, you will try, and then like 15 minutes later, we will talk about it, right? The tasks that I gave you for the shell and so on were like, you have it and you do it, and I don't care, right? But the ones which we'll do next week is a little bit more interactive. It will be a sequence of like trial and error, or like trying things out and like getting stuck or being able to solve something, right? So it will be a little bit more interactive. And I think it's a little bit more fun. I like the second half a little bit more than the first one, right? So we will see how it goes. Okay, so that's it. I will stop recording now and try to finish